Division of Physics and Applied Physics. He teaches PH 3403, which is the Cosmology module, and he's also the club advisor of our club, NTU. So without further ado, I'll pass the time over to Dr. Leek.
Yeah, okay. Okay, so good evening. So maybe let's just start slowly. I don't have that many slides, but actually the slides are somewhat technical. Let me just tell you a little bit more about myself for a short while. Okay. Why did I choose to do physics for my PhD? Okay, it's actually because of astronomy. Okay, because when I was young, I was in the library reading astronomy books actually. So that was I think even before secondary school. So why I want to do physics is because I want to understand all the stuff that I was reading in astronomy. Because when you read an astronomy book, it is basically like a book of facts. Okay? So they'll tell you, oh, this is like this is like this. You either accept or you don't accept, right? Because you can't check. An astronomy textbook is just a book of facts. Okay? So you can't really question, you can't really confirm or disprove it. So that's why I choose to do physics for my PhD. Okay? To be very frank, when I was in secondary school and in JC, my chemistry score is actually better than my physics score. So physics was not my strongest subject. Actually, even for biology, my secondary school biology is one of the best subjects. Physics was like second or third only. Okay, but the reason is I want to know all this. Okay, so that's why I did physics for my PhD. Okay, and there are a few telescopes in my office also, but due to my job, I don't have time to play with them for quite a while already. Okay, so what we're going to go through here today is, yes, something like what I teach in the course actually, but a very summarized and hopefully easily understandable version. The point is, we want to understand cosmology itself. Okay, so I'll tell you how we explore this thing, because it is such a grand question, right? Cosmology, entire universe. Okay, so such a grand question. How do humans even try to tackle and understand this? So let me give you the basic understanding of that. Okay. Okay, so anyway, due to COVID, of course, I haven't been to any astronomy trip for more than 2 years already. So yeah, last time I used to go Malaysia at least once a year at least. Before that, when I was doing PhD, I go to Malaysia like 4 times a year. So, but now pandemic, okay. So we see how, okay, because recently I heard the news saying that they might want to start a CVTL service from here to Desaru. So, but Desaru must have changed a lot. So I haven't been there for a number of years already. So we'll see how. Okay, so to start off, of course, we have to, throw down a definition of cosmology. Okay, so cosmology is, yes, the study of the evolution of the entire universe. That means we want to know the universe from birth to the end. The end may or may not be a death. Okay, or if the universe dies, we want to know how it dies. Okay, Does it die in a cold way or does it die in a hot way? So that's the idea of cosmology, the entire universe itself. Okay. There are theories in physics that actually predict multiverse. I mean, aside from all those movies you've been watching, okay, especially the one that will come out in May. So what happens is, yes, there are theories in physics that do predict multiverse. So if the theory contains multiverse, then cosmology will encompass the evolution of the entire multiverse. Okay. Okay, so let's throw down other words because these are very similar words in astronomy. So, what is astrophysics? Because you might have heard of these terms before and they are very confusing. Okay, so if cosmology is the evolution of the entire universe, so what is astrophysics? Basically, astrophysics means, okay, application of anything in physics to astronomy, anything. Okay, which basically includes, like for example, say nuclear physics. You apply to astronomy, that will be the nuclear fusion in the core of the stars. Okay, so that's included as well. Okay, so cosmology is basically under astrophysics, because as you will see later that cosmology is also the application of physics, okay, to the astronomical phenomena, i.e. the whole universe. Okay. Then what is astronomy? So all these very similar terms. Okay. Actually, in the scientific community, astronomy and astrophysics are basically almost two interchangeable words. Okay, they really treat them as interchangeable words. But in my opinion, I prefer to think of astronomy as made of four subtopics: astrophysics, astrochemistry, astrobiology, and astrogeology. So when you think of astrochemistry, there will be the application of chemistry to astronomical phenomena. There's a lot, okay? Because in the gas molecules, in the gas cloud, those dark nebula and stuff, there's actually chemical processes going on. Okay, they form molecules, even though the temperature is ridiculously low, but it still occurs because you have a huge amount of dark cool gas. So even though the reaction rate is ridiculously low due to the low temperature, you still have a lot of chemical processes happening. So astrobiology, which is mostly related to formation of life, or formation of even like amino acids in let's say in the solar system. Okay, astrogeology, so of course geology phenomena like volcanoes, tectonic movements. Okay, so let's come back to cosmology. Okay, so in order to tackle this grand question, entire universe as a whole, so we need to observe the entire universe and see as a whole what does it do, okay? How does the whole universe look like? Okay. So we will zoom out from Earth. Okay, the mouse is not very visible. Yeah. Somehow the laser doesn't show. Okay. So never mind. So we'll start from the Earth. We will zoom out. So it is part of the solar system. So we are the third planet from the Sun. Then you zoom out further to the nearby stars, so the interstellar neighborhood. And you zoom out to the entire Milky Way galaxy. Okay. Then you zoom out further to the local galactic group of galaxies. and you zoom out further to the Virgo supercluster of galaxies, and you zoom out further to local superclusters, i.e. every spot here is like its own supercluster. Then you zoom out to the entire universe. So the question is, what do we observe as a whole in the entire universe? So the universe is, roughly speaking, homogeneous and isotropic. So we will make these terms clearer later. Okay. And later when we will build a theory for the universe, it will be based on this assumption. So based on galaxy surveys, so you survey out to a so-called redshift of 0.3, 0.25, 82,000 galaxies, you roughly see that the distribution of galaxies is like quite uniform, random. Okay? I know it doesn't look very random, but reasonably random. Okay? You know, you're trying to tackle a big question, so you have to make a reasonable assumption. Okay? So the most reasonable assumption is to say that, okay, it is uniformly distributed, pretty random. Okay? And one more piece of evidence is when we look at the cosmic microwave background radiation, which is basically the leftover heat from the creation of the universe. We see that it is actually quite uniform. This blue and red represent different intensities, like the peak and the trough. So the peak and the trough difference is very, very tiny. Okay, 0.0 something Kelvin's temperature difference only. So it is very uniform. And the spacecraft in 1989 measured a very blurred picture. Then the mapping done in 2001 and 2010 shows that yes, the leftover heat in the universe is really very uniform with very tiny differences in temperature only. Very tiny, less than 1 Kelvin, much less than 1 Kelvin difference. So there's a very uniform background heat in the universe. So overall, the universe is pretty homogeneous, pretty isotropic. So now we come to the actual meanings of these terms. Okay. So based on the observations I showed you just now, so we can come to this statement or assumption to use. So the universe is homogeneous, meaning it looks the same from any point in the universe. That means I stand at this galaxy, I look all around me, looks homogeneous. I go to another galaxy, I look around me, it also looks homogeneous. It looks the same. That means everything is like distributed uniformly. And we also assume that it is isotropic, meaning that in any direction it looks the same. So in this direction, it looks like there's uniform distribution. Now I turn to this direction, it also looks like there is uniform distribution. Or if I look at this direction, it is also like having a uniform distribution. Okay, so I say again, homogeneity means any point in the universe looks the same. That means you are on this galaxy or that galaxy, doesn't matter. Okay, it looks the same. And isotropy means you have one particular point, you look in all directions, they look the same. So there's no specific direction. Every direction just looks the same. So based on this, we can then formulate a model or theory to try to understand the universe as a whole. Okay, so subsequently, the slides are going to get a bit more technical. Okay, so just bear with me. So now we are going to translate this principle into something workable, that is a model of the universe. So we think of three-dimensional space, 3 galaxies, let's say. Okay, of course there's a lot more. So we just take 3 sample galaxies, and then we think of drawing a triangle. So we want to formulate homogeneity and isotropy into an expression. Okay. So to fulfill homogeneity and isotropy, this triangle should only stretch or shrink. That means it keeps the same shape. So that in a future time or in a previous time, the triangle is only bigger or smaller. So it is still the same, right? In the future time, the triangle is, let's say, bigger. It's still homogeneous and isotropic. Okay? So based on that, okay, the Pythagoras theorem for this 3D space can only be like this. That it scales in time. That means there's an overall scaling factor. That means it doubles or halves or quadruples. So the entire thing stretches or shrinks. So A is called the scale factor because obvious reason, right? Okay. Okay, and just a fun historical tidbit here. Einstein himself, you know, he's the guy who came up with the theory suitable to discuss cosmology, but he himself is a little misguided. So he believed in a static universe. Okay, his belief, he doesn't know any observational results. It's just his own belief. He thinks that the universe is static. That means it doesn't change, doesn't move. Everything is just stuck there, like frozen in time. Okay? So, of course, you can have a frozen universe, static universe, that the scale factor doesn't change. It's constant, okay, sure. But obviously that is an unlikely choice because if scale factor can change or it's a function of time can change, then A being a constant is like unlikely choice. But he insisted that, okay, then Edwin Hubble, okay, went to measure the distances to galaxies, and then he found that the galaxies are actually moving away. So the universe is obviously not frozen, not static. Okay? So Einstein calls it the greatest blunder of his life. Okay? So not sure why he insisted.
Yeah, you can see how exciting it is in terms of natural philosophy.
Yeah, possibly because humans have their own beliefs as well, right? So that's why he has his own belief that that sort of overshadows his scientific practice. Okay. Yeah. Okay. So just an historical tidbit here. Okay. Okay. So now we are actually going to construct the space-time itself. Yeah, we are really going to do that. Okay. So we want to construct a 4-dimensional space-time, but the 3-dimensional space is homogeneous and isotropic. So to do that properly, okay, we take reference from special relativity, which is the simplified version of Einstein's general relativity. That's all you need to know. So the Pythagoras theorem in special relativity is like this. Okay. Basically, the 4D length square is your 3D length square with a negative times square part. Negative. So this negative part is because special relativity has something called Lorentz transformation. So in order for the Pythagoras theorem to respect the Lorentz transformation, that thing has to be a negative. So this is a unusual Pythagoras theorem. Normally Pythagoras theorem is plus plus plus. But this one has to be a negative because we have to respect the rules in special relativity. Okay? For the time part. So now, just now we already established that the homogeneous and isotropic Pythagoras theorem is, scale factor and length square, 3D length square. So now to make it 4D, you just need to slap on the time part, following the negative sign. So just slap it on. Okay. Just slap it on like that. Okay. In fact, this expression is almost the answer already. So from what I teach in the course 3403, we do derive the full expression, and it's practically this expression, very much the same. So intuitively you can understand this quite well. So let me show you the actual answer that I derived in my course. So it is almost like that. So the time part is negative because we have to follow the rules. And then this is the scale factor, so there's a square, so it's slightly different. And then this is the 3D length square. Okay, so it's almost the same answer. Okay, and so this result is called the Franklin-Robertson-Walker metric. Okay, and this parameter here, K, is a geometry parameter. Scale factor is the only unknown. Okay, scale factor is the only unknown. So, you don't need to take my course and you can already guess a almost the same expression as the one that I derived in my course. So just by physical intuition, you can get quite far. Okay, so this geometry parameter K, so let me tell you what they entail. So K can be plus 1, minus 1, or 0. So when K is plus 1, it is what we call a closed geometry. Closed geometry, meaning it is like a sphere, surface of a sphere. Okay? What I'm saying is that this geometry means all the points on the surface are inside and outside the sphere, no count. That means if you live in this geometry, that means let's say you're on Earth, this geometry. So when we say the closed geometry, it's like you have two persons on the equator, and then both of you walk towards the South Pole, let's say. Initially, you and your friends start off as parallel, so you can hold two rulers and make them parallel or what. And after walking, you find that you all actually get closer and closer together. So we say this is closed geometry. Okay? So yeah, you can try that, but you need to walk a very long distance before you realize you get closer.
It's something to do with geodesics.
Okay, the word will appear later, but this can be a geodesic, it doesn't need to be a geodesic. Yeah. So yeah, don't worry, we'll come to that later. So the other geometry is a flat geometry. So if you start off as parallel lines, then you and your friend will continue to be parallel forever. Okay? And for open geometry, again, you and your friend can start off as parallel, and then when you start walking, and then you'll find that you get further and further apart. Okay? So we pause here and summarize a bit. Okay? That means if I assume that the universe is homogeneous and isotropic, based on all this mathematics that we worked out, there are only 3 geometries possible for the universe. So throw dice to see which one we are in, right? So it's a throw dice situation now. So the max has already told us that it's just one of the 3. Okay, so if the universe is homogeneous, isotropic, this is what we have. Okay, so yes, we will now make a quick digression to general relativity. One slide. Okay, so what happens is we actually want to solve for the scale factor. We want to solve it because that's the only unknown. Come on, if you solve it, you will have the full knowledge of the theory that we are working with. So to solve it, you will be using general relativity. Okay, that's what we do in the course. Okay, so to solve for the scale factor using general relativity, so we have to have a quick summary of general relativity now. The good news is general relativity is actually an elegant theory. I'm not saying it's a simple theory. I'm saying it's elegant, meaning its summary is short and sweet. There are just 2 important equations. Just that when I'm teaching the course, deriving these 2 equations take about almost half a semester. So it's a sweet theory, but it takes a long journey to get to the sweet spot. Okay? Okay, so the 2 equations are, yes, I literally showed them to you. You don't have to understand any of this. Einstein's equation looks like some Gabra up there. Sure. Okay, let's just throw in the meaning. The left-hand side stands for the geometry and curvature of space-time. That's all you need to know. The right-hand side, this T thing, is the source of gravity. So when you learn about Newton's law of gravity, the source of gravity is just mass. You have mass, you have gravitational attraction. Full stop. Newton's law is like that. That's it. Mass, attract, finish. But Einstein realized that it's not just mass that is the source of gravity. It turns out that you have actually 10 things here. 10. So mass is just one of them. Okay? So a variety of sources of gravity. A variety. Okay? So in short, this equation tells us that, okay, you specify your sources of gravity and you solve for the geometry here using this equation. That's it. So matter tells space-time how to curve. So you throw down your planet, then the curvature will be solved from this equation. Okay? But yeah, solving this equation can be a few weeks in the semester. Okay? And historically speaking, when Einstein first wrote down this equation in 1915, he actually said, okay, the equations are so freaking complicated, probably no one can solve it. They just chuck it aside. Then 1 year later, 1916, so somebody sent a letter to him, not email, no email in those days. Sent a letter to him saying that, yeah, he has found a solution. And Einstein was like, oh, okay, can be solved. And the best part was that guy solved it while he was fighting World War I in the trenches. So quite a bit of free time there. After digging the trench, he got time to do such things. Okay, so the second equation is called the geodesic equation. So just now somebody has mentioned this word. So again, a bunch of Gabra there. So okay, let me just throw you the meaning. This X thing represents the trajectory of particles, and this gamma thing, capital gamma thing, has the geometry of space-time inside. So in short, the meaning of this second equation is the curved space-time tells matter how to move. So these two equations are very intuitive. First equation, you put in your galaxies, black holes, and sources of gravity, then you get the curvature of space-time. You solve for it. Now you have the curvature of space-time. You will see how the planet moves, or you will see how the stars move in this curvy space-time. So the two equations are interlinked. Okay, and that's all for general relativity. Two equations. Okay, just that in my course, derivation of two equations, as I mentioned, takes a few weeks of the semester to do it.
But are those equations inverses of each other?
I'm sorry?
Are those equations inverses of each other?
No. As you can see, the meaning is not inverse. Basically, okay, for the first equation, the first equation says that you specify your stuff first. You specify your galaxies and so on, then you get the curvature. So now you have a curved space-time. Then now you can put rockets, planets, or humans, and then you can see how they move in this curvy space-time. So it's not exactly inverse. It's more like one leads to the other. Yeah. Okay? Okay. So what we are going to do is we are going to solve for the scale factor, okay, using Einstein's equation. So on PowerPoint, of course, when you say solve on PowerPoint, means nothing is going to happen now. Okay, just like every lecture you attended, right? On PowerPoint, solving means clicking, click, solve. Okay, no, that's what solving means, right? Using PowerPoint. So remind you that the left-hand side is the geometry and curvature. The right-hand side will be the sources of gravity. So for cosmology, the sources of gravity will be assumed to be the galaxies. I mean, there are so many galaxies. Okay. In fact, we will even include the dark matter and all those dark energy stuff. So we treat the galaxies like gas molecules with density rho and pressure P. Okay? Something like ideal gas. Okay? We call it ideal fluid, but almost the same. Because that's the simplest thing. You treat the whole universe like ideal gas. And each so-called molecule is actually a galaxy. Okay? That's how we can progress. Okay? So just now we have the FRW metric, which already encompasses homogeneity and isotropy. So now we plug it in. So the scale factor will be here. So plug in and then somehow solve. And I will show you the results. So once you plug in, you solve, you will give the famous FLRW equations. Okay, I don't know how to pronounce some of the names here, so I better don't try. Okay, this should be a French word. So I never picked French before, so I better don't try. Okay. Okay. So the first equation for A looks something like this. The second equation for A looks something like this. Okay, which comes up from Einstein's equation. And we can actually get even more equations. These equations are very important. The density as a function of the scale factor. So in this case, this first density is density of matter, including dark matter, how it changes with the scale factor. The second one is the density of radiation. That means the radiation, the EM radiation in the whole universe, how it changes with the scale factor. So 8 or -4. And for vacuum energy, which is the so-called dark energy, that means the energy in the empty universe, is actually a constant density. So all this can be derived. Okay? So it's actually very important because we immediately get one consequence we'll see later. So just a reminder that ordinary matter, dark matter together is about 32% dark energy, which is the energy of the empty universe, is 68% of the universe. Okay, so yes, there's energy in empty space. Okay, and it's actually a majority. Okay.
But so far there's been no general solution to the Einstein's problem.
No, because we are using a specific version, right? We are saying homogeneous isotropic version. So of course, there's no general solution because it's too difficult to solve. So we say our version is with the homogeneous restriction and isotropic restriction. This particular assumption is being used for this model. Okay? Yeah, because we can't solve for the general version. Too bad. So we will take a certain set of assumptions and work with it. Okay, so here we mentioned that the densities are related to the scale factor, and this is actually a very important prediction now. So the radiation is a to the power of -4. Matter density is 8 to the power -3. Vacuum density, that means the energy density of empty space, is a constant. So we sketch graphs, and then we realize that when A changes, A is your scale factor. So when A gets bigger, the universe should get bigger. Okay? This means the densities will change as the universe changes in size. Okay? So at the beginning, radiation might be the dominant component, but because it is 8 to the power -4, so as A gets bigger, it decreases quickly. So radiation density will drop very quickly. Okay? And then it will be dominated by matter, but because matter decreases as A to the power -3, so it drops also. Eventually, after a long time, this vacuum density dominates because every other component decreased below the constant. So this means the behavior of the universe breaks up into 3 eras. The radiation dominated era. So in the early era, how the universe behaves depends on the radiation, the EM radiation, because it dominates. Then after that, the matter component will dominate the behavior of the universe. Matter component means galaxies and dark matter. Then when the universe gets very old, dark energy will dominate because the other densities have decreased so much. So the good news is it's very easy to tell the fate of the universe already because dark energy is going to dominate for sure and forever it will dominate. So it's actually easy to tell that the universe, the dark energy or the vacuum energy is going to dominate, and then it's going to cause an expansion. So looks like we are just headed for an expansion. Okay. So with all those theory part done, I can now show you what is the standard Big Bang theory, which is assuming that the vacuum energy is 0. So we assume that the matter dominates most of the universe. we assume that, okay? So we set the radiation component to 0, okay, for max friendliness as well, okay? So in my course, yeah, the max is not very friendly once you have other components coming in, okay? So in short, when we solve for the scale factor for the 3 geometries, it will look like that. So these 3 curves represent the scale factor as a function of time for the different geometries. So if you have the open geometry, so the scale factor will just increase. That means expand and just expand. Just keep on increasing, that's all. There's nothing much happening, it's just increasing, okay? And then for the flat geometry, it will expand, it will just expand. So the A is proportional to this thing, okay? So it will just keep on expanding non-stop, but it doesn't expand as fast as the other case, okay? And for the closed geometry, okay, the universe will actually shrink. The A actually increases and then decreases. That means the universe will expand and then decrease, close back. So when it closes back, then there's what we call a big crunch. That means it bang and then crunch. Okay? In fact, the equations do show that after the crunch, there will be another one. So it will be like those bumpy graph kind of. Okay. So these are the Big Bang curves from any textbook. Okay. So as you can see, the journey of how we understand this is actually quite straightforward. We assume the universe is homogeneous, isotropic. Then we came up with, we end up with those 3 kinds of geometries that we have. Scale factor is the only unknown, so we solve it with Einstein's equation because that's the best theory of gravity, right? How else you want to solve for the scale factor? Using the best theory, right? So we solve for it, and then we get the so-called evolution of the universe from beginning to end. So for those 2 universes, their ending is just, expansion forever. And then for the closed geometry, the ending is a big crunch. So yeah, so that's how we tackle this very big question. Evolution of the entire universe. Okay? Okay, last slide. Okay, so now we will take stock. That means we saw the Big Bang theory, those 3 graphs, those are the standard Big Bang graphs. So now let's take stock of whether this Big Bang theory is actually relevant or not. So it is relevant because, again, when you look at the cosmic background radiation, this is the leftover heat from the creation of the universe. There is no better explanation for this heat. Put it that way. Because they found this heat in the background of the whole universe. So if you have a better explanation of where this heat comes from, go ahead, propose. So if there's no better proposal, then the best explanation is this background heat is the background heat left over from creation, from Big Bang. Okay? So that's the best explanation. Okay? So therefore it's justified by this cosmic microwave background radiation. But of course this Big Bang theory has problems. Okay? It is not a perfect theory. We make a number of assumptions. So the first contradictory information came from the cosmic microwave background radiation. So it's like cosmic microwave background radiation support you and then slap you in the face again. Okay? So the contradiction is, I mentioned that the temperature of the cosmic background radiation is almost uniform, very tiny differences in temperature. Okay, so it's in thermal equilibrium. We call this thermal equilibrium, same temperature. So, but the universe is expanding. So, is there time for the universe to reach thermal equilibrium? It's like we have a gas. Let's say you have a gas with two different temperatures. Let's say you mix two gases together at two different temperatures. And then you let the volume of the container expand. Then, does it have enough time for it to mix and reach a thermal equilibrium temperature? Does it have time? May or may not have, right? So, in this case, it shouldn't actually reach thermal equilibrium. Because going by the expansion of the universe, there doesn't seem to be enough time for the universe to be mixed enough to reach thermal equilibrium. So, the uniform temperature there is actually a question mark. Since when there is time for it to reach thermal equilibrium while the universe is expanding? So, what happens is that the remedy, the so-called remedy, was to change the Big Bang story a little bit to add in an inflationary era. That means we physicists cheat ourselves. Okay? We cheat ourselves by saying that after Big Bang, the universe was not so big. Not so big. It was expanding but not so big, smaller. Okay? So there's time to reach thermal equilibrium. Then, after it reached thermal equilibrium, there was a period where it suddenly expands a lot faster, inflation. So we changed the story to fit the narrative. Okay? So again, this kind of theory, is subjected to all kinds of arguments. Because you couldn't possibly verify this, right? Because somebody just going to change the story of Big Bang. Say, oh, you add in another era, okay, sure. Yeah. Then if there's new evidence, then you can add on more stuff. So that's just the suggested knowledge as of now, okay? Okay, so in 1998, the dark energy, vacuum energy was discovered, okay? So what happens is I show you that it is 68% of the universe. So the problem is basically everything in the universe is going to be controlled by this dark energy now because it is basically the main component. So how our universe will change is basically just dependent on one component only, the dark energy. Okay? So we have to change the equations to fit that story. Okay, and lastly, we started off with homogeneous and isotropic space. But from the galaxy pictures, you know this is just an approximation. Okay, so we do need to include some inhomogeneity and anisotropy. Okay, but then general relativity will become really complicated. Okay, so this is a question for PhD level. It's a PhD level project. Okay, so with that, we are at the end of the talk. Okay, so
Okay, thank you, Dr. Leek. Okay, so now is the Q&A portion. So we'll open the floor to any questions. Okay, I can ask the first question. I have a few questions.
Okay, sure.
So, know that there are three types of geometry. So, which geometry are we in?
Okay, what happens is that there is actually, there things in the theory that actually strongly suggest that we are in a flat version. Okay, because based on other implications in the theory, it seems like that if, let's say we measure ourselves as flat universe, it seems like, okay, let me put it more simply. The geometry doesn't change. So if you start with one version of the geometry, your universe will be stuck in this kind of geometry forever. So right now, in terms of measurements, it is pointing towards the flat geometry. Okay? And also, based on theory, there are other implications that seems to indicate that we are also in a flat geometry also. So that seems to be the case right now. But I tell you, when I look at the graph, it's like all those, you do experiments in the lab, right? The graph together with the error bar, everything overlaps everything. And then it's like, oh, okay, the best fit line is the flat universe geometry. Okay, sure. So we did data, we did experimental analysis in this flat geometry.
Okay, so I've actually heard there are some people who say that before the Big Bang there was actually another universe. Before our Big Bang there was another universe. So that would imply that the geometry is k equals to -1.
-1, the open one. The +1 is the one with the that means if it is a bang crunch, then yeah, we may be in a cycle. But how do we, even though we are in a cycle, actually we don't really know, because it's like one cycle wipes out everything. So if you are in a new cycle, Big Bang, Big Crunch, you won't know how many previous Big Bangs and crunches you have. The information is not there anymore. It's wiped out. So yeah, it's a bit hard to even verify that. Yeah. So could be. So nobody's right or wrong.
So if the multiverse is true, and just say that we can travel to different universes, so some of them will have been around for like forever, and some might be new universe.
Oh, okay. If you really want to go there, then you need to learn magic spell. No, but what happens is that basically the idea why physics includes multiverse in the theory is because when you try to think about the seed for Big Bang, the question is, if the seed for Big Bang is valid, then why should there be one seed? Okay? So the seed actually has to do with quantum, but I don't want to bring that word in. So basically, if you can seed one Big Bang, why can't you seed more? SEED, seed. Okay? So that is not out of the question. So that's why we say the multiverse is not ruled out. Okay? And another version of multiverse theory is when one Big Bang occurs, the universe can also bang into sectors. That means it's possible that from one bang, okay, the universe breaks itself up into different sectors, separated by so-called cracks in space-time. Okay, that is becoming like Spider-Man already. So we see the cracks itself. So, but physics do allow that. It's what we call domain walls. Okay, so it's something like okay, maybe the best example is when you freeze ice from water to ice. So if you freeze it like too quickly or what, the ice cube may not be very nice. It may be cracked. That means there might be chunk chunks of ice cube with cracks between the ice. You freeze it too fast. So each so-called broken chunk of ice is like a sector, like its own universe. So that is one version of multiverse. So there is just one bank, but during the bank it forms sectors, it forms separate sections of a universe. So that can happen also. So, but again, the problem is we have no way to tell also, because according to our observation, we cannot even see to the end of our universe, so we don't know whether there is something beyond or not. We just cannot see beyond. Yeah, so that's the problem. So a lot of speculations on that. Yeah.
Anybody has any questions?
I have a question.
Yeah.
Why do we assume dark energy to be constant?
Oh no. Actually, we didn't assume. It was actually solved from the equation itself. Yeah. So in my course, is it the lecture notes or tutorial? I think it's the lecture notes, not tutorial. Yeah. So it's solved. So it's because of the nature of the material. It turns out that when you solve it, it turns out to be a constant. So it's a bit bizarre, meaning that the universe expands. So we say the density is constant. So that is beginning to sound a bit strange. The volume gets bigger, but density is constant. That means something is created. And yes, indeed, that the dark energy actually is in some sense created to keep the density constant. So this is not an assumption, it's what we saw. Yeah. So too bad we are forced to accept that because that's what the equations tell us. Yeah.
Question. So
Yeah.
just now you said that there's 3 components of dominance, right? So which one are they?
Which one, sorry?
Which one are we now? The component of dominance.
The era, right?
Yeah.
Okay, right now, I think not better. Slow. Okay, anyway, let me just continue. So we are more or less in the era of dark energy domination. So that means we are at the border between matter and dark energy domination, more or less around there. And it seems like we just stepped into the dark energy domination era. So which is a bit sad, meaning that the universe will just expand forever. So it's like a very anticlimactic story. Okay, it's just a sad, cold death of the universe. And it's just begun. So the sad, cold death of the universe has just begun. So we should be around here, around here. We just entered this era.
Are we able to know the exact time again?
Of course, all these densities. That means if you can measure the densities, then you know where you are. So based on the measurement now, it seems to be in that sense of the matter density is almost the same as dark energy densities around here. It's almost equal. So probably dark energy a little bit more. So that's how we know where we are. Yeah. Not where we are, when we are. Yeah. So that's why a lot of information in astronomy has to come from observations. Otherwise, everything is just paper talk. Take Einstein's theory, talk whatever you want.
Are there any implications on outside of what we observe that we are not factoring in?
Sorry, I can't catch the last one.
Are there any implications on what we cannot observe? And we are not factoring in.
Okay, things that we cannot observe but may implicate us. Actually, there's a very, very interesting cosmology problem. It's one of the top 10 cosmology problems. You can Google such things. You can Google top 10 cosmology problems. There's actually an issue that comes from quantum, not from cosmology, but it actually will turn the whole universe upside down if it really happens. It turns out that from the other theory, quantum, that we may not be in the most stable situation. The whole universe may not be in the most stable state here. Meaning, if it really happens, if it really happens, then the universe might so-called, okay, when we use the word quantum, we also use the word tunneling. We may move to a more stable state according to the rules of quantum. If it really happens, then what happens is that the properties of the whole universe will change. Meaning that you can think of it as there will be a spreading kind of influence that the whole universe property will change if we really move to a more stable state. That means if we are not in a more stable state, then there is a chance that we will move to a more stable state any time, because quantum is like random. It may or may not happen, random. It's just a probability tagged onto this. Whether it happens today or tomorrow, we don't know. There's just a numerical probability tagged onto it, that's all. So if it really happens, then the properties of the universe will change, spreading over the entire universe, then it may turn the whole universe upside down. It's fascinating. I hope it doesn't happen in my lifetime.
What would be the difference?
Because according to that quantum theory, some things might change. For example, let's say the gravitational field strength may change a little, or the Coulomb attraction, the charges repel, unlike charges attract, the strength may also change a little bit. So if that really changes a little bit, then we may or may not exist anymore. That means atoms might blow apart. If atoms blow apart, then we are done, finished. So that is actually a very scary thought. So very good for Hollywood movies, but we don't know whether it will really happen or not. But you can Google top 10 problems in cosmology. So that is one of the so-called problems in cosmology, which actually comes from a theory that has nothing to do with cosmology. Okay? Yeah, it's a question that somehow, your question somehow over answer your question. Yeah.
Can I ask one more question?
Yeah, sure. Go ahead.
Now that the standard model has been completed from the discovery of the Higgs boson,
Yeah.
are there any progress on gravity?
Okay. If you are specifically talking about gravity, right? Basically, what happens is that the main machine that is checking all those particle physics stuff, the machine CERN, the Large Hadron Collider at CERN, they are checking all this. Higgs boson was discovered 10 years ago. Scary. Okay? Imagine 2012 is 10 years ago, right? So what happens is, as of now, their checking has been very fruitless, very boring. they are supposed to, find abnormalities or what, but they found nothing. Every time they try to check against the standard model, it works very well. So they got this scared. It's like, oh, come on, show me something wrong. Okay? If the experiments fit the theory so well, then that's the end of the game already. But so far that's the trend. That is, everything fits the theory so well. That is being measured there, and it fits so well. So, because in other theories, there's actually more than one Higgs particle and so on. But they simply just know there's no evidence for more Higgs particle. And then you try to measure the properties of that Higgs particle, and it fits the theory so well. So, I also offer FRP projects for my students on particle physics, and I tell them this. I said this is the disclaimer, okay? That I don't know, maybe standard model somehow seems to be working so well, then we don't see anything new, then this area of research might be a bit dangerous to embark on. Because imagine a FRP student carry out research into this, after that sign PhD, 4 years of PhD, then towards the end of the 4 years, then they say, oh, okay, standard model is perfect. Then that poor guy will become jobless the moment you graduate. Or he has to change field immediately after graduation, or whether he will graduate or not is a problem also. So I tell him to be a bit more careful. Yeah, that's the sad truth. So we see how, okay? Okay, I actually didn't answer his part of gravity. With regards to gravity, there's nothing. So people talk about string theory and all, but string theory is very stuck. Very, very stuck. Okay? String theory is not a theory that is over-predicting. Let me explain what it means. It's becoming a theory that is not giving proper predictions. For example, Newton's second law is F equals to ma. Okay? And suppose there's a theory that says, oh, the theory predicts Newton's second law is F equals to m to the power anything, a to the power anything. So is that a prediction? Not really, man. Because yeah, the correct answer fits in, but your prediction covers too many possibilities. It's like m to the power of anything, a to the power of anything. Okay, then sure. Then you say your theory will predict Newton's second law because your prediction is so great, so wide. Anything also counts. So string theory is like that now, so it's not really predicting anything. It's like saying anything is a prediction already. And of course, people say, oh, that string theory is true, but I don't like this kind of argument now, because you are not saying that basically m to the power of anything, a to the power of anything is a valid theory or throws out a valid prediction, then that's a bit too much already. Okay, it's a catch-all theory, catch every version. So it lost predictability already. Yeah. Okay, so yeah, any more? Just feel free to ask. Yeah. So how many of you are in physics? Okay, so about half. So okay. So if you are intending to take my course 3403, okay, what I show you here in those slides is basically covered in the last 3 weeks of the course. That means what I presented in the last 45 minutes needs 3 weeks of calculation to carry them out. So, so that's a little warning on that. Okay? Because the problem with learning physics is like that. The mathematical details always come in as a tsunami of mathematics. Wow, calculate. Okay? And then what I show you is basically all the physics. So you have already seen all the physics in 3 weeks of the semester. The rest will be the mathematical details. So for those doing physics majors, my so-called advice to you is try to separate the maths from the physics, because every time I ask like year 3 student, year 2, year 3 student, like, oh, you've done this course, so what have you learned? And he said, there was a lot of calculations. I'm not sure what I learned, but I just calculate, and then I submit my homework, and then I prepare for exam, and then somehow everything passed. Oh, okay, sure. So life is like a dream. So in order to appreciate the things that you have learned, it's best to try to set aside or be able to distinguish the maths portion of it and the physics portion of things. Then you will be able to appreciate the stuff that you learn better. Okay, so hopefully that helps. Yeah.